We're told the number of bacteria present in a culture at time t, which is given in hours, obeys this model, n of t equal 1000 e to the 0.01 t. This is in function notation. If you prefer, you can just think of it as n equal 1000 e to the 0.01 t. It's the same general idea. So the first question is, we want to determine the number of bacteria at t equals 0 hours. So this just means this is when we started to look at this sample of bacteria. So if we plug in t equals 0, we get 1000 e to the 0.01 times 0. Now, in multiplying in the exponent, we just end up with 0. The key is, what's e to the 0? A non-zero number to the 0th power is always 1. So this just ends up being 1000 times 1, which is 1000. And the point of this problem is to show you that in this type of a model where we have an exponential with a number times the exponential portion, the number in front is the amount that we're starting with when we start to look at this. Okay, so B, what's population after 4 hours? Well, here we're going to have to calculate a little bit. So this is 1000 e to the 0.01 times 4. I'm just going to use the calculator. Watch the exponents. The entire multiplication needs to be in the exponent, and the only thing that gets the exponent is the e. So 1000 e to the, in parentheses, 0.01 times 4, and your parentheses. And this comes out to be approximately 1040 point, I'm going to write now here 81, but this is the number of bacteria. So we should inherently round this to a whole number. Now there's two schools of thought. I will take either one. It says 0.8, so you might think, oh, I'm going to round up to 1041. The other school of thought, and again I'll take either one, you don't have to give me both, just give one or the other, is that if this is only 0.8 of a bacteria, I don't have that full bacteria, so it must be 1040. So either one of those answers would be fine. Now you do need to watch, because sometimes with these type, when we're looking at something like bacteria, instead of having the number, it's a measurement in terms of weight. So if it's given to you in grams, then it is allowed to use a decimal portion with that, unless you're told to round to the nearest whole gram. Okay, so the next one, when will the number of bacteria reach 1700? So that's what we want to end up with. And we have that equal to 1000 e to the 0.01 t. Our old classic exponential equation. Start by dividing by 1000. And again, I'm going to put this at the calculator at the end. I can reduce this if I want to. I don't have to. I see immediately, though, that 100 goes into both of those, leaving me with 17/10. Now to undo the exponential, I'm going to use the natural log. It works out beautifully in this situation because my exponential has base e, and the natural log is also base e. So when I take a natural log of e to something, these cancel each other out, and I'm just left with that exponent, which is 0.01 t. Then when I divide, natural log of 17/10 divided by 0.01. Can use my calculator. Natural log of 17/10 in the parentheses divided by 0.01. I'm getting about 53. Now it doesn't tell me how long to round to. I see 0.062. I'm just going to say 0.06, and this was in hours. Okay, so a little more than 53 hours, and my population is going to be to 1700. Okay, part D. When will the population double? Okay, so do a few things here. You can look at it and say, aha, I've started with 1000. So when I double, I'll end up with 2000. 1000 e to the 0.01 t. And we're going to solve this very similar to what we had up here, just change 1700 to 2000. But notice when you first do the division by 1000, you end up with 2 equal e to the 0.01 t. This is because of doubling. Okay, and it's very similar to how we did this with exponential equations when we were doing interest. And notice that we get 2 equal just the exponential, no number in front if we're cutting straight to this. Okay, so just be careful, make sure you're consistent and you pay attention to what you're doing here. Either 2,000 equal 1,000 times the exponential, divide to get 2, or just 2 equal the exponential with no number in front. From here we use logs again, and once again, since the exponential is base e, the right hand side is going to simplify very nice to give us just that exponent, 0.01t. I'm not being consistent on writing my 0 in front of the decimal, but I should. Okay, and then now divide. T is going to be the natural log of 2 divided by 0.01. And when I put that in the calculator, about 69.3 hours. And it makes sense that it's longer, because doubling gets us to 2,000. The previous problem we were only getting to 1,700.